Hello and welcome. In this video, we're going to talk about how to find the volume created when we rotate in an area and there's actually a hole on the inside, and this is called the washer method. So let's go ahead and jump right in. Before we jump back into volume, what I actually want you to do is go ahead and find the area bounded between these two curves using the strategies that we learned in 7.1. So go ahead and pause the video and then unpause the video and see how you did. So we learned previously that the area is just going to be the integral of the top minus the bottom over the bounds at which we're looking. So the bounds we can tell from the graph. With respect to x, our bounds are going to be -1 and 2. The top function, if I trace the top of this curve, is the line. So that's going to be x plus 2. The bottom function is going to be this piece of parabola. And then we can go ahead and find the antiderivative here, which is going to be x squared over 2 plus 2x minus x to the third over 3. And we're going to evaluate that from -1 to 2. If we plug in 2, we're going to get 2 plus 4 minus 8/3 minus, if we plug in -1, 1/2 minus 2 plus 8/3 plus 1/3. And if we distribute this negative and combine like terms, we're going to end up with 9/2 units squared. So this is a review of what we covered in 7.1, finding the area between two curves. But what if we wanted to take this same area that we're looking about and talk about what we've been talking about, talk about rotating it around the x-axis to create volume? So let's clear some space so we can think about this. Here we go. So if we were to rotate this little teardrop looking guy around the axes here, we would have a gap. We would have empty space that's forming here and empty space that's forming here. So all of this red, when we rotate it, would be empty. And what that's doing, if you think about this from the top, is it's creating a little hole. So we're having volume that's rotated, creating around, but there's a little gap that's forming in the middle that's not being filled in because of this red gap here. So this is where we need to keep in mind what our top and our bottom function are, just like we did with area, but how that's forming the radius that's being rotated around our axes or our line. The way that we account for this in our formula is that we will find pi r squared, just as we did before, but now we're going to be talking about sort of a big R and a little r. So we need to still find pi r squared, but we need to identify between our two functions which is the big one and which is the small one. So let's look at this example and actually work through the volume now. We have already talked about the bounds for this integral being from -1 to 2. That doesn't change if we are finding the volume instead of the area. We still have the same two x values. What we need to look at now is what are our two r values. And since we are rotating around the x-axis, that's why this is dx. We need our function to be in terms of x, and we need to figure out which is the big one and which is the small one. So let me try and erase here so that it's easier to look at this. The big function is the one that's forming a larger radius with the x-axis because that's where we're rotating it. So this line here is like my big R. That length is forming the top of my entire area no matter where I am. So when I rotate it, that area is always going to be bigger. And that is the line, just like we did with the area, so that function is going to come first in our integral. Little r is going to be the smaller area, the area that's forming below, which is going to be our other function, our quadratic. So really ask yourself and draw those lines to make yourself sort of see that radius. That radius is rotating around the axes to create this donut-looking washer. And that's how we have to decide which is our outside or our big R and which is our inside or our little r. So go ahead and simplify this integral and then work through to find the antiderivative, and then unpause the video to see how you did. So first we want to simplify this integral, then we want to find the antiderivative, then we want to substitute in our bounds and simplify. So here's the step with direct substitution, and then if we combine like terms and find a common denominator, we end up with 72 pi over 5 units cubed. So I really want you to keep in mind, where is my larger radius that's forming from the curve to the place that I'm rotating? Where's my smaller radius? So that we can set up still the integral of pi r squared, but now we have big R minus little r squared. And we're integrating with respect to either dx or dy, depending on how we're rotating. Let's look at a few more examples together. Okay, for this example, we're gonna find the volume when we rotate around the x-axis. And what I want you to do is go ahead and pause the video and do a quick sketch of the square root of x and x squared. So here's my quick sketch. And what I can tell from this graph, even though it's a little sloppy, I can tell what the bounds are, which if I couldn't tell what the bounds are, just as a reminder, we can always just set these two functions equal to each other, square both sides, x to the fourth minus x equals 0, so x times x cubed minus 1 equals 0, and we get 0 and 1. But I actually think we can tell those 2 points from our graph. We can tell that the bottom function, or little r, is going to be the quadratic. It's under the other function. And if you're not sure, plug in a number that is below, or that is in between 0 and 1 and check. That means that big R is going to be the square root. So let's go ahead and set up our integral. We're finding the volume from 0 of pi times the integral from 0 to 1 of big R, which is the square root of x squared, minus little r, which is x squared squared with respect to x. All right, go ahead and pause the video and work through this integration on your own, and then unpause the video and see how you did. So you should have gotten the antiderivative is x squared over 2 minus x to the 5th over 5. And if I plug in 1, I get 1/2 minus 1/5. And if I plug in 0, I get 0. So I can find a common denominator, which would be 10, and this is going to give me 3 pi over 10 units cubed. For the next 2 examples, we're really just going to focus on creating a sketch of a graph and setting up, and then we will wrap up with one more example where we actually work through the whole problem start to finish. Okay, so go ahead and graph the quadratic here, and there's a couple ways you can do that. You can graph it using finding the axis of symmetry and then plugging that in to find the vertex. You could also graph that using calculus. As a reminder, you could find the derivative and figure out where the derivative is 0. That's going to give you the x value of your vertex. So I'm actually going to do it each way on each of these problems, but I'm going to have you adjust one thing. I'm going to have you make on number 3 this a minus 2x. That's going to make our lives a lot easier. Okay, so to sketch the quadratic for number 2, we're looking at, I'm going to just write it as y equals negative x squared minus 2x plus 6. The axis of symmetry is going to be x equals 2 over 2 times negative 1, so x equals negative 1. If we plug negative 1 into our quadratic, we get 7. So negative 1, 7 is our vertex. It's opening downward. 2, 3, 4. So we can do a quick sketch, running out of space here, of our graph. The line has a y-intercept of 6, and then it's going up 1 and over 1, so the line is slicing in right here. Hopefully your graphs on paper look a little bit nicer, but we can tell here that the area that's being bounded between the 2 curves is this area here. We're being told that we're rotating around the x-axis in the directions that you are a little bit cut off on the top. So let's see if we can figure out what we need to know. Let's talk about the bounds first. The bounds are going to be where these 2 functions cross. So x plus 6 equals negative x squared minus 2x plus 6. If we get everything on the same side, we're going to end up with x squared plus 3x equals 0. And if we factor this, we're going to get x equals -3 and 0. So the bounds for our integral, which I'm going to come up here, volume equals pi times the integral from -3 to 0. And now we just need to figure out what our functions are. So since there is a gap between our curve and the x-axis, which is all of this empty space here, that is what's telling us that when we rotate it, there's going to be a hole. This is going to be a washer or a donut here. So we need to figure out what is big R and what is small r. So looking at my curve, I'm going to draw a line from the x-axis until I hit the outside piece of the function. And that means I'm hitting the quadratic. The quadratic is our top function. So -x² minus 2x plus 6. And we're going to square that. And we're going to subtract our second function, which is x plus 6, quantity squared dx. So this would be the integral that we would use to find the volume if we rotate this piece of area around the x-axis. So let's go ahead and set up number 3. There we go. Now we have a little bit more space. I'm actually going to use calculus to do my sketch of the graph for number 3. So make sure you note that I'm going to change this problem to be -2x instead of +2x. So we talked about how you can find the axis of symmetry in the vertex so that you can graph here, but you can also find the derivative and use the derivative to figure out where the extrema are. So the derivative of this would be -2x plus -2. That's going to be 0 when x equals 1. X equals 1, that's what makes this 0. So the x value of the vertex is 1, and if I plug 1 in, I'm going to get 5 minus 2 minus 1, so I'm going to get 1, 3. So I can graph the point 1, 3, and then I can use the fact that this doesn't have any stretches or shrinks to plot a couple more points, 2, 3, 4, and get a sketch of my quadratic. And then the line y equals x plus 1 is just going to have a slope of 1. And again, and maybe if I had a nice grid or wasn't graphing on an iPad, I'd be able to have a better idea of what these intersections would be. But I can see my area. I can tell what's on the top and what's on the bottom. So let's start with that. We know that volume is going to be pi times something squared. And right now, since we're rotating around the x-axis, we're going to have dx. The bounds we're going to find in a minute, but can you identify which is the big R and which is the small r? So go ahead and draw a line from the x-axis, that's where we're rotating, to the outside of the shaded region. That's going to be your r, and that's forming with the quadratic. So our big R is -x² minus 2x plus 5, and we're going to square that. That means our little r has to be the line, so minus little r, which is x plus 1 quantity squared. Now let's go ahead and find our bounds by hand. So we're going to set these two things equal to each other, -x² plus minus 2x plus 5 equals x plus 1. And then we're going to get everything on the same side. This is going to be x² plus 3x minus 4. And this is going to factor and give us the two values, -4 and +1. So -4 to +1. So the volume created when we take this little teardrop shape that we're rotating around the axes is going to be pi times the integral from -4 to 1 of the quadratic squared minus the line squared. Let's wrap up with one last example that we're actually going to work all the way through start to finish. All right, so we're going to be rotating around the x-axis, the area formed between x equals 1 and the square root of x plus 3. So go ahead and pause the video and do a quick sketch of those two graphs. So x equals 1 is going to be a vertical line, and g of x equals the square root of x plus 3 is going to be that square root function that's forming this piece of red area. So I want you to ask yourself, if I rotate this around the x-axis, is there a hole? Is there a gap? And I'm hoping that you see that the answer to that question is no. If I go from the axes up to my curve, I'm covering that entire area. So I don't have to have big R minus little r, or you can think big R is my function and little r is just 0. So we can set up the integral, volume equals pi times the integral of, I'm actually going to write minus 0 squared because I want you to see the setup is the same. And our function is going to be the square root of x plus 3, and then we're going to square that. And then our bounds, I do feel like I can see them from the graph. Our bounds are going to be x equals -3 to x equals 1. And if we integrate here, we're going to get pi times, actually, before I integrate, I'm going to simplify this. The square root of x plus 3 quantity squared is just x plus 3. And then this is going to give me pi times x squared over 2 plus 3x, and we're evaluating that from -3 to 1. And this is going to give me 1/2 plus 3 minus 9 over 2 minus 9. And if I combine like terms and simplify here, we're going to end up with 8 pi units cubed. So the big idea in all the different pieces that we have covered for volume for 7.2 is, can you look at the graph and identify the area, or can you create a graph that shows the area that we're going to rotate? Is there a gap between the area and the line that we're going to rotate it around? If so, our integral is going to have 2 different radius that we're squaring. If not, it's only going to have 1. Can you find the bounds where they intersect? And can you integrate pi r squared to come up with that volume? So go ahead and write down any questions you have, and I look forward to supporting you on this. Thanks for listening.